Okay, so this lecture is on thin films and interference. It's section 10.1 in your textbook. So a good example of what a thin film is in physics would be a soap bubble. So you see a shimmer on a soap bubble, and that kind of color that's flowing across the surface of the soap bubble is caused by an interference pattern that is typical of a thin film. So a thin film would be, if you think of the thickness of that soap bubble, it's very small, very thin. So it's going to cause this type of color distortion on top. It's a combination of constructive and destructive interference that depends on the phase difference of the waves. So here's a sample. Here's something to try to get us to understand this. It says in diagram A, we have a wave passing from a slow medium into a fast medium. So both the reflected and the transmitted wave are on the same side of the spring if that happens. When we have a wave passing from a fast medium into a slow medium, though, the wave is the partially reflected wave is inverted. So this change or inversion that occurs when a wave reflects off of an interference with a slower medium is a property of all waves, including light. And it is the inversion that results in either the constructive or destructive interference of light in a thin film. So let's consider a very thin film. So this is where the thickness is much, much less than the wavelength of light. Both rays originate from the same source, so they're initially in phase, but ray 1 will be inverted when it's reflected, whereas ray 2 will not. So because the film is very thin, the extra distance traveled by ray 2 isn't very much. So, and with the two rays being 180 degrees out of phase, they have destructive interference. So this causes if you look at a soap bubble, because of the effect of gravity, the soap bubble is thinnest at the top and thickest at the bottom. So this causes the top of the soap bubble to be dark. It's the region where it's most thin. At regions where we're a little bit thicker, so this is when lambda is about a quarter, we end up having a path difference that is a bit more noticeable. So the path difference, if we're a quarter wavelength out of phase, the path difference is a half wavelength. This gives us constructive interference. We start to have bright ranges. But when we're at when the thickness of the film is then at about a half of the wavelength, the path difference is a wavelength, and now we start to have destructive interference. So what we end up noticing is that destructive interference occurs every time we're at either a wavelength or a half wavelength away, and constructive interference occurs at a quarter wavelength, 3/4 wavelength, 5/4 wavelength, and so on. That's the kind of pattern we have. So copy this slide down. This helps to explain thin films and interference. And we'll talk about it a little bit more here. It says a soap film produces constructive interference of light of wavelength 500 nanometers. A second film produces constructive interference of light with a wavelength of 600 nanometers. So which film is thicker? And in the case of this, the second material would be thicker because our constructive interference has to occur when we're at lambda over 4, 3/4 lambda over 4. So the larger the wavelength, the thicker the material. Here we're asked to say what type of interference happens in this case, and because we have these patterns are basically 180 degrees out of phase, it would be destructive. Using the wave theory to explain how the interference pattern from part A is caused, we say because the film is very thin, the extra distance traveled by ray 2 is negligible, and the two rays are about 180 degrees out of phase, so they interfere destructively. Next says, would it be possible to coat an object with a very thin film to make it invisible in white light? And in this case, you can't really, because if you're coating this, what you need to, this destructive interference pattern that you want to see, it would need to work for various wavelengths. And white light itself is, or rather the thin film interference occurs only for one wavelength. White light itself is a component light of many different wavelengths. We're going to get into some applications of thin films. One of them is Reflectin, which is a protein that's produced by cephalopods like cuttlefish, squids, and octopi. So Reflectin, it basically is it can be used as like an invisibility cloak. It allows it gives that shininess to a cephalopod, and depending on the type of light that's most prevalent, it can make a fish of this type, or a cephalopod, really not a fish, to appear to be, or make it more difficult to see, so appear to be invisible within the water. It reflects a type of light that will make it look like it's not there. Butterflies, like the blue morpho butterflies, have a certain pigmentation that allows them to have kind of like holographic wings. And as part of this, they actually have small little holes in the scales of their wings that produces this. And the reasons for this could be many. We're not in a biology course, but I think part of it is the more colorful something is, the more likely an animal thinks that it is poisonous. So that's one of the uses in nature, another use in nature. For some non-natural uses, if you look at your money, now we have money that uses thin films to give that holographic effect. Very difficult to replicate that. So anytime we have something that we want to make secure, we would use thin films. I won't read this any further, but if you want, you can kind of read through. You'll notice thin films, in terms of a DVD or a CD, you can actually kind of see a thin film in action by kind of tilting it with the light. Holograms are another aspect of thin films. So holograms can be produced by thin films, although I'm not really familiar. It's one thing that they give here as a sample or an example. So next it says, is this soap bubble of uniform thickness? And I've already explained about the gravity idea. It's not of uniform thickness. We have various thicknesses here. We have the thinnest part at the top and the thickest part at the bottom. And we see a change in the interference pattern of the thin films throughout because of that. So what's producing the color? So because light itself is made up of different wavelengths, we're seeing the different colors because the different wavelengths of light that are constructively interfering at those times tend to be the wavelengths of those colors. So that's why we see that effect, that holographic effect of a thin film of a bubble, a soap bubble in a light source. So there's novelty uses as well. Thin films are used in to make things kind of look like holograms, which people tend to like the look of. But another application on glasses, thin films can be used to reflect some of the light off the surface of glasses to make it easier to see. So it says here again, as such, eyeglass manufacturers make use of destructive interference caused by thin films to prevent reflection on glasses. Another thing, it says, by applying a coating of carefully designed thickness to the outer surface of eyeglasses, specific wavelengths of light can be canceled out. A similar procedure is used in the lenses of cameras. So lastly, I'd like you to copy this down. Applications of thin films, we talked about quite a bit. The novelty of it, there's eyeglasses, camera lenses. For currency or for any sort of protective, something that we don't want to be replicated. Optical invisibility is another thing that's kind of being looked at, using Reflectin to see if we can make something reflect all wavelengths of light. And there's a ... there because we're still working on other applications of this as well.